So we've been talking about the wave-particle duality of electrons, and then we're going to talk about the wave behavior of electrons. De Broglie proposed in 1924 that particles can have wave-like character in addition to their particle character. We see the wave nature of an electron most clearly in electron diffraction, which is a lot like the light diffraction that we saw with the double slit experiment. So what's very, very trippy about this is that the interference pattern we see is not caused by pairs of electrons interfering with each other. It's not one electron wave interfering with another electron wave. It's one electron interfering with itself as it goes through two slits at the same time, because it's a wave, not just a particle. Doesn't seem possible. So this experiment was done in 1927. Very similar to light diffraction, we have a source of electron beams, so the electrons shoot across here, and we have two closely placed slits, and as the electrons go through, they create an interference pattern just like light does. Now you can't see this, but you can detect it using a detector. And I'll have to see if I can find it. My husband found this great video that actually shows the results in real time of this experiment. So we see this interference pattern, and that's caused by electrons behaving as waves. If the electrons were just particles like baseballs, and we're sending those at this screen here, they would either hit the screen and bounce off or something, or they would go through the slit and continue in a straight line and make a bright line on the detector. We'd have two beams there. This is what would be expected for a particle. So the diffraction pattern we see is a proof that electrons behave as waves. And the wave nature is an inherent property of individual electrons. It's not a group of electrons together being a wave. It's a single electron being a wave. So de Broglie predicted the wavelength of a particle was inversely proportional to its velocity. And so this is known as the de Broglie relation. The wavelength is equal to Planck's constant divided by the mass times the velocity. And here, this is a lowercase italic v. That's a v for velocity, not nu for frequency. I know, holy crap is right. So this is v, velocity, as opposed to that which is frequency. I know, crap, right? Planck's constant, thankfully, is the same as it always is. So we can use this relation to solve problems like this. What's the velocity of an electron that has a de Broglie wavelength approximately the length of a chemical bond? Assume this length to be 1.2 times 10 to the minus 10 meters. So they're saying that for this relation, the wavelength of this particle is 1.2 times 10 to the minus 10 meters. And they're asking, what is the velocity? Well, what does the equation say? Lambda equals h over mv. So lambda equals h over mv, velocity. So we're trying to find the velocity. That's this guy right here. This equation has fractions in it, so be careful. I still see people messing up the rearranging of this. So rearranging this, we get v is equal to h over m lambda. And if you need help with the algebra there, I'd be happy to help you outside of lecture. Well, what's h? H is Planck's constant, 6.626 times 10 to the minus 34 joules times second. And the mass is the mass of an electron. Hey Siri, what's the mass of an electron?
The electron is a subatomic particle, symbol or Greek letter beta, whose electric charge is -1 elementary charge. Would you like to hear more?
Yes, what is the mass?
Mass is both a property of a physical body and a measure of its resistance to acceleration when a net force is applied. Shall I continue?
No. What is the mass of an electron?
The electron is a subatomic particle, symbol or Greek letter beta, whose electric charge is -1 elementary charge. Would you like to hear more?
No, Siri, you're not listening to me.
My apologies. Please try again and tell me what were you looking for?
Maybe later. Go to your crate, Siri. I've been spending too much time with the dog. Okay, electron, mass. You know, she usually comes through for me. Okay, 9.11 times 10 to the minus 31 kilograms. I don't expect you to remember that. I don't remember that. Don't use it very often. Now, we do need to be a little bit careful with units here, and on an exam, I'm not going to try to trick you with units on a question like this. Kilogram is the base unit of mass in the SI system, and if we're doing things with joules and the units are doing crazy stuff, we need kilograms, meters, seconds. We can't have grams. So the kilograms are appropriate here. So we can plug this in, 6.626 times 10 to the minus 34 joule seconds. I know that joule is a kilogram meter squared per second squared.
Okay, right.
Yeah. So if this was an exam question, I don't expect you to know the mass of the electron. I would give it to you somewhere in kilograms because that's what you need. And the answer would not be something where I was trying to trick you and see, oh, did they convert it to grams? And I wouldn't do that. 10 to the minus 31 kilograms. And lambda is 1.2 times 10 to the minus 10 meters. Didn't leave myself enough space. 6.626 E minus 34. I graded worksheet 6 last night, and some of you have the equation written out correctly, but then you executed it incorrectly in your calculator, and that's a real shame to do all the hard work and end up with the wrong answer. So that's why I recommend always doing a calculation twice. Clear the calculator, do it again. If you get the same answer, at least you're consistent in your wrongness. So that's up to the decimal point. This should have 3 significant figures, no 2, because of the mass. And some of you are still getting the sign on your scientific notation exponents backwards. Is this a small number or a big number? It's a big number. How do I feel about big paychecks? I feel positive. I feel good about those, right? Positive. So this needs a positive exponent. I'm seeing people giving this as 6.1 times 10 to the minus something. Yeah.
Is that a decimal right after the first 6, or is that just the extended 6?
That's just the 6 kind of slopping over. Like there. Yeah, the decimal point is not actually written, but it'd be right there. I'll just write down all the stupid digits. This is what my calculator is showing me. So 6.1 times 10 to the 1, 2, 3, 4, 5, 6, and that's a positive 6. The units, a joule is a kilogram meters squared per second squared, and that's multiplied by seconds, and then we're dividing by kilograms and meters. The kilograms cancel, the second cancels one of those, this meter cancels one of those, we end up with meters per second. That unit business there is not something I expect you to be proficient at. I show you that just because I know that some of you care about stuff like that, and so I don't want you to think that I'm just doing voodoo or something with units. Is that a reasonable velocity for an electron? How do we know? Well, in general, the smaller something is, the faster it moves. The larger it is, the slower, right? So because an electron is really, really small, I expect its velocity in meters per second to be really high. If you came up with 6 times 10 to the negative 6 meters per second, that would be a red flag. You should say, wait a minute, that's super, super slow. I can walk faster than that. Yeah.
What should the meters and the electron be the numerator? Better question is how come it's not in the numerator?
Well, when I rearrange the equation, I get the mass and the velocity in the denominator. Just out. That's what algebra tells me.
You've done here to bring it over to the other side.
Well, I can talk to you about rearranging the equation outside of lecture, but I have 45 slides to get through in an hour. So. Any other questions? Here's a conceptual problem. Since quantum mechanical theory is universal, it applies to all objects regardless of size. Therefore, according to the de Broglie relation, a thrown baseball should also exhibit wave properties. Why don't we observe such properties at the ballpark? When you throw a baseball, why don't you see it doing a sine wave as it goes through the air? Now, that's a question that I would expect as an open-ended question to be really, really tough for you to answer. But we have 3 choices. Because of the baseball's large mass, its de Broglie wavelength is minuscule and insignificant compared to the baseball's size. Since baseballs do not have any charge, quantum mechanics does not apply to them, or quantum mechanics does not apply to baseballs. Well, what does the first part of this question say? The theory is universal. So that kind of negates the second 2, right? B and C. Does A make sense? Well, we just learned that the wavelength is inversely proportional to the mass, right? A large object has a very small wavelength. A smaller object has a larger wavelength. Let's double check that. So here's the mass. Sorry, pointer, come back. Here's the mass, and here's the wavelength. So if one gets bigger, the other gets smaller. So compared to an electron, a baseball is ginormous. It's like a planet or a solar system even. It's huge, right? So if it is much larger in mass, then its wavelength must be much smaller. Compared to its size, the wavelength of a baseball is so small you can't see it. So yeah, the baseball does have a wavelength, but it's so small it doesn't matter, and so we don't even ever think about it. Does that make sense? This would not be a test question, but I think it's helpful to think about. Any questions? Oh, the uncertainty principle. So an electron is a wave and an electron is a particle. But when we try to observe the wave nature of the electron, we cannot observe its particle nature. So there is this superposition where the electron is a wave and a particle at the same time, but if it's observed, we force it to collapse into one or the other. We observe its wave nature from the interference pattern. We can observe its particle nature when we see its position, like which slit in that experiment the electron is passing through. So I'll come back to this, but here's that same experiment. We've got the electron beam coming at these two slits, and what we normally see is a series of bright and dark lines in interference pattern. Here, we're shining a laser beam right on the other side of the slit so that we can detect which slit does the electron go through. The electron is a particle. We can detect which slit it went through, but when we do that, we force it to behave like a particle, and it no longer behaves like a wave, and we see the pattern here change from a diffraction pattern to two lines. Take the laser away, the diffraction pattern comes back. That should be just disturbing. Like, how the heck, right? We're not even going to try to understand that. It's like, the universe is really weird. So the wave and particle nature of the electron are complementary properties, and what this means is the more you know about one, the less you can know about the other. You just can't. So Heisenberg came up with sort of an equation for this. This is called Heisenberg's uncertainty principle. And the most important thing about this is the concept of it. What this is saying is that delta x, so that's the uncertainty in the position of the electron, times the mass times the uncertainty in the velocity, must be greater than or equal to Planck's constant divided by 4 pi. We're definitely not going into how did he come up with this or why is it true. But we have uncertainty in position, uncertainty in velocity. The more you know about one, the less you know about the other. Yes? Question? That V is velocity, yeah. I need to come up with a way to be more clear with that. They are, in this font, they are different, but not when you don't see them next to each other. That's velocity. So we cannot simultaneously measure the position and the velocity of an electron. We could say, okay, at that instant, the electron was right here, but then we can't know anything. If we know exactly where it was, then we can't know anything about its velocity. Or we could know that it's moving at this speed, but then we can't say where it is. Or we could know a little bit about the velocity and a little bit about the position, but you can't know both. And it's not just that we don't have the technology, it's just it's a fundamental principle that you cannot know both. So which statement best summarizes the uncertainty principle? Both the position and the velocity of an electron can be accurately known at the same instant. No, that's kind of the opposite. Either the position or the velocity of an electron can be accurately known at the same instant. That sounds more reasonable. That's not obviously wrong. Or C, neither the position nor the velocity of an electron can be accurately known at the same instant. Now, the choice between those two is a bit tricky. We can know one if we don't know the other. So we're not saying that we can't know either of them. Especially with electron beams, we can measure the velocity of the electrons. That's not a problem. But then we can't say exactly where they are. So we can know one or the other. Of course, we can also know none. Like right now, electron X, I have no idea where he is or what he's doing, right? But it's B. Any questions about that? So according to classical physics, particles move in a path determined by the particle's velocity, position, and the forces acting on it. This is called determinacy. The present determines the future. You throw a baseball and you can look at its trajectory, the wind blowing on it, gravity pulling on it, how fast it's moving, and you can predict what's going to happen. That's comfortable classical physics. That's the kind of physics I enjoy. But because we cannot know both the position and the velocity of an electron, we cannot predict the path it will follow. So this is called indeterminacy. The future can only be predicted statistically. So the best we can do is describe the probability that the electron will be found in a particular region. And we do this using statistical functions. We make a probability distribution map. So here's classical determinacy. Here we've got this baseball being hit, and we've got the trajectory. We've got gravity, and here's the position of the ball, the velocity, and we can predict where it's going to go. And even if you've had no formal education at all, you can learn to catch a baseball that's hit to you in the outfield, right? Because your brain is an amazing computer, and your brain learns to predict where that ball's going to go. Some people are better at it than others, but you can predict what's going to happen with that ball. This is what happens with the electron. So here, not the baseball being hit, but baseball being pitched. So the pitcher pitches the baseball, does it the same way, the ball goes to the same place every time. Here, if we're pitching the electron in the same way, it goes to a different place every time. Because electrons are squirrely, they're quantumly small. So we can see that in the center here, there's a higher probability of the electron being found, but it might be out here. And is it possible for the electron to go up here and through the net and hit that guy in the face? Yeah, it could do that. Now, is it likely? No, but it could. And so we can look at this, the quantum mechanical strike zone, the number of particles versus the distance from the center. And so we see that more of them are close to the center, and as you move away, the number of them decreases, but we cannot predict exactly what's going to happen with that electron.